Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to some important theorems and their corollaries from calculus. Today we are going to discuss one very famous, result known as differentiability at a point implies continuity at that point. Differentiability at a point implies continuity at that point. Of course, differentiability of a function and continuity of a function. So let's state the result precisely. It says that if f of x is differentiable at x equal to a, then f of x is continuous at x equal to a. Let's prove this. What I'll show here, I'll just show this, the condition of continuity, that limit x goes to a of f of x is equal to f of a. So I'll show this. So mathematically I can write something which is f of x minus f of a. This can be written as x minus a times f of x minus f of a divided by x minus a. Now these both sides are same. Now you just need to apply limit on both sides. Limit x goes to a to this side, also limit x goes to a to this side. Now you can see that I can operate this limit on f of x and this f of a. But this f of a is constant because it's a number, it's a value. So this f of a, because limit will not do anything to something which is constant. But I can apply this limit on the product of these functions like separately, because product of limit of products of functions is product of limits of functions. So I can use that idea, f of x minus f of a divided by x minus a. So you can see this is 0 and this is nothing but derivative of f at a by definition. So this is going to be equal to x goes to a of f of x minus f of a, which give me 0 to right side, and limit f of x when x goes to a minus f of a equal to 0, and you can easily write from here that limit of function when x goes to a of f of x is equal to f of a, and this is sufficient to say that differentiability of a function at point a implies continuity at that point. For f must be defined at that point because that's the simplest continuities assumption, one of the assumptions for continuity. So f of x is, if f of x is differentiable at x equal to a, then f of x is continuous at x equal to a. We just proved. What is going to be interesting, so you can see many examples. For example, f of x equal to sine x, this function is differentiable at x equal to 0, so you can say that it must be continuous at x equal to 0. So when there is a differentiability, there must be continuity. But what is important from here is you can think of contrapositive of this statement. Contrapositive. So contrapositive for the above statement says that, so this is if statement and then this is then statement. So you just negate then statement and the if statement will be negated then. So my this is my statement P and this is my statement Q. So P implies Q was this statement. What I need to construct is I need to construct its contrapositive, which is not Q implies not P. Or I can say that if f of x is not continuous at x equal to a, then f of x is not differentiable at x equal to a. So if a function is not continuous, then it is not going to be differentiable easily. Thought. For example, you can think of a Heaviside function h of x equal to, so it says 1 when x is I think greater than equal to 0 and 0 when x is less than 0. So you can see that the graph of the function look like this. So it's 0 if x is less than equal to 0, so this, and it is 1 when x is greater than equal to 0. So you can see that at x equal to 0, h of x is not continuous. So it must not be differentiable, because not continuity implies not differentiability. You can also see many other very interesting examples. Say f of x equal to 1 by x. You all know that at x equal to 0, this function is not continuous. So at x equal to 0, this is not differentiable also. You can also see g of x equal to 1 over x minus 1. So at x equal to 1, this function is not continuous, so it must not be differentiable also. Sine function, if you recall this, sine of x, this says that minus 1 when x is less than 0, 0 when x is 0, 1 when x is greater than 0. You can check its graph. It is discontinuous at 0, and it is discontinuous at 0, so it is not differentiable at 0. Then we have a very interesting pulse function. Pulse function says that it is 1 when x is between a and b, 0 if x is less than a or x is greater than b. You can also plot this pulse function. Let's say here it is a, here it is b. So it is 1 on this a to b and it is 0 otherwise. So you can see that at a and b it is not continuous, so it is also not differentiable. So you can have many other examples.